Okay, here we go, Chapter 6. All right, in Chapter 6, we're going to introduce the set of rational numbers. That's to include fractions. Here's the definition. The set of Q, that's the special blackboard notation for the set of rational numbers, is defined by A over B such that A and B are elements of rational numbers and B is equal to 0. I see that I have got a mistake and I don't really want to stop here, but what this should actually be is integers. Okay, so it's not we can't define rational numbers of rational numbers. So this rational numbers is made up of integers. We can have positive and negative fractions in rational numbers. Okay, the element A, so the numerator, the number on top is called the numerator, and element B is called the denominator. And the set of rational numbers is collectively called fractions. It is to be noted that fractions start being a very heavy part of the curriculum in third grade and then just keeps on going. But really in third grade is where they set up all of their real understanding of fractions. If you know anyone in your life, trust me, I know plenty of people in my life that always confuse the rules of fractions and stuff like that. Well, that's because probably wasn't presented to them in the appropriate way in third grade, or at least in the right order or with enough patience or enough times for them to get set with the appropriate rules for fractions. It's really easy to mess them up. Anyway, let's get started. The parts to whole model is really the main idea as far as introducing fractions, and I have demonstrated that in 3 different kind of models here. The first one would be the bar model, where you would draw out a bar that is separated in the number that your wholes are. And if we look at this particular problem right here, this is demonstrating 3. So we have 1, 2, 3 out of 5. So this fraction is 3 of 5. Here we have the distance model where we're using a number line. You can see where I have from 0 to 1, and then I have broken it into 5 sections here, and we have 1, 2, 3, 4, 5. So this fraction here is 2/5. As a side note, when you do break things up using hash marks, to get the right number, you want n minus 1 lines in your range. Okay, so if we were trying to break this up into fourths, I would need 3 lines to get 1, 2, 3, 4. Okay, so that's a good little thing to just know in your pocket, so you're not always counting, and you can kind of do it with some confidence and figure out how many lines you're going to have to put in there so that you can get them set as nicely as you can. It's not always possible when you're hand drawing things to get it all nice, that's for sure. And then finally down here I have the set model, and this could be anything, any shape or whatever. I use circles because they were easy, and out of the 5, we would have here 4 out of 5, 4 being our clear ones. Now the set model definitely sets open for some ambiguity, especially the way that I did this. This could also be seen as 1 out of 5 if we were considering the colored 1 as 1. Okay, alrighty. So there's some rules for the parts of the whole. Well, not really rules, but really good guidelines. So for all of your whole numbers A and B, where B is not equal to 0, you want to consider the following here. When you're putting together a fraction of A over B, a good way to think about this and to have your students think about this is it's always the part over the whole. Okay, so first off, you need to consider what the whole is in question and know that that's going to go on the bottom. Also, of the fraction. Also, the whole is divided into equal part of B units, like every little unit. So if we have our whole here, whatever this is here is the length of B. So the next one would be 2B, and the next one would be 3B, and whatever, going on and on and on. We don't really know what this number is here, right? I'm just giving an idea here. So it's equal parts of B units, and we get B from the denominator that tells us how many wholes there are. And the number A is the number of the parts selected, so how many we want on top. So equal size parts of a whole, when they're divided, are called congruent pieces, and that means that they are of equal shape and size. So let's get a little bit more vocabulary here. A fraction is called proper. It's considered proper if the numerator is greater than the denominator. So the value of the numerator is less than the denominator. I know I just said it the wrong way, and I apologize. I said it backwards, but the numerator has to be smaller than the denominator. And an example could be like 11/13. Okay. An improper fraction happens when the numerator is greater than the denominator. Okay, and when the numerator is greater than the denominator, then we get this improper fraction. An example of that would be, say, 13/11, numerator being greater than the denominator. A fraction that has a numerator that's always 1, that's 1, is considered a unit fraction. So every denominator has its own unit fraction. So the unit fraction for 2 is 1/2. Unit fraction for 3 is 1/3, unit fraction for 4 is 1/4, and so forth. So as you can see, every single denominator would have its own unit fraction. Okay, and another thing that I wanted to point out here, and this is kind of like a little mix here, but a big point of confusion that students have, even often as they go into college, because they don't get a clear understanding of it when they're in their formative math years, is that it doesn't matter if a negative is in the numerator or a negative is in the denominator, or if it is out front of the entire fraction. This all means that this is negative. So it all means that there is basically a -1. So we could look at it this way, as -1 times A over B, or this could be A over -1 times B, or -1 times A over B. These all are equivalent. Okay, so an important thing is for students to know where to actually, place numbers on a number line. And once we start getting into fractions, then sometimes all bets are off. It's really important to set them up for success, and this is a good way to do it. First off, I'm going to label these out. This is my 0, so this makes this -1, and this makes this -2. Making this 1 and making this 2. So let's take a look at the directions here. It says, first, break each segment in equal parts the size of the denominator. So the denominator here is 4. So we need to use 4 minus 1 marks to divide it. So we need 3. So I'm going to put 3 marks in here. And I'll do my best to get them nicely placed, but Okay, so we get that all done. And now it says, starting at 0, demonstrate A sections of the 1 over B size pieces. So right now, 1 over B is 1/4 size pieces, and the A in this problem is 7. Okay, so we're going to start right here. And we're going to go 7 of these spots. 1, 2, 3, 4, 5, 6, 7. So right here is where we have positive 7/4 on the number line. So that allows us to get positive 7/4. And the other thing that we were asked to demonstrate is negative 7/4. Now, to demonstrate the negative, it can be done 2 ways. We've already identified the positive, and sometimes for students, it's really important to just stay very consistent until they're extremely strong with a skill. So for me, in introducing this, I would use the idea of the opposites here, but one thing that you could do that's not the idea of the opposites is we could just go in the negative 7 direction, right? So we could go negative 7 of these. 1, 2, 3, 4, 5, 6, 7. So that could get you to the spot as well. But if you're freshly introducing this, or maybe your students are not quite grasping the idea of negative numbers, which right now you might think is insane that they couldn't, but just stay open to anyone not understanding anything that you might find obvious or whatever. So the other option here, which is to reflect across the 0, you want to lean into the fact that these two numbers are opposites of each other because of the signs. So we could mirror this. We know that this is where positive 7/4 is, so we could come across here and find the mirrored spot and know that this is where negative 7/4 is. So that's a couple of different ways that you can help your students in placing fractions. Another big thing, a very important thing, is understanding the equivalency of fractions. And there's a lot of tools out there that you will have, I would hope that you would have access to manipulative wise. But a couple of the main things and like the easiest and cheapest things and things that you can make for yourself in the classroom or print off is something called fraction strips. And these can be made, they don't necessarily have to be done with 1 1/2. We could use any kinds of denominators here as long as they're going to show equivalency. But this is a good basic one. I just pulled this off the internet and just put it here so I didn't have to make it. Another thing that happens quite often in the classroom and gives the students a really nice hands-on thing is something called paper folding. You'll find that paper folding is a big way to model a lot of math ideas, especially once we get into dealing with fractions and stuff like that. So you won't be using, say, base 10 blocks as much as you'll be using maybe individual blocks and or this idea of paper folding or fraction wheels or fraction strips or things like that. The paper folding, I need you to kind of use your imagination here. So on this first example here, I'm just going to color in one piece. Now, the thing that makes paper folding so effective is because all the paper is exactly the same size. So you will be comparing the exact same whole, so to speak, and it just depends on the matter of the number of parts you break that whole into. And so it's real consistent. and effective, and the kids also get to do folding, and you can talk about hot dog folds and hamburger folds and get some other kind of content pushed in there during math class. So if we just take a look at here and we want to maybe explore the equivalence of 1/3 and 2/6, we could see that we could notice that those are the same length. They're the same size, so they're equivalent. And you can do these really intricately. I did not want to break it into any more than 6 parts, but you know, however big of a piece of paper you have and you can get them to get enough folds in there is how many pieces out that you can work these guys. All right, let's see what's next. Okay, so the next thing is talking about the fundamental law of fractions. And remember, anytime the word fundamental and law are together, either of those words, it means it is really, really important. So here it is. It says if A over B is a fraction and n is not equal to 0, this should also say B is not equal to 0 as well, then A over B is equal to n times A over n times B. In other words, as long as you multiply, the numerator and the denominator by the same number, you have not changed the fraction. Okay, and we'll talk about more about why that gets there, but it all comes down to being in simplified form. But one other thing I want to make mention to you is n divided by n, those guys cancel out and it's equal to 1. You guys know that 2 over 2 is equal to 1 and 17 over 17 is equal to 1. And we're just kind of just being real literal about it in this formula. All right, so it's kind of like a tricky way of multiplying by 1. But in the same way, you can also take things away. You can add in by multiplying by n over n, but you can also get the exact same thing when you take out an n over n. And I'll show you here on this simplifying fractions example. So here we start off with 60 over 210. The first thing off is when you notice that they both end in 0, you know that they both have multiples of 10. So I just separated it, and these literally can cancel out here, but I was being real literal and wanted to put this in total factored form. Okay, and so I found the prime factors, and then I just put them in order. Because a lot of times students can't think in order, but it's important to reorder your work. It's important to show extra steps and things like that, because it helps keep your eye on the prize, keeps you from losing a step or whatever. And then we can literally cancel out the things that are common. So we have a 2 over a 2. Well, those cancel out because they're equal to a fancy 1. We have 3 on top and a 3 on bottom. Those also cancel out because that makes a fancy 1. And we have a 5 on top and a 5 on bottom. Those two cancel out and make a fancy 1. And we are just left with this 1, 2 on top and this 1, 7 on the bottom. So 60 over 210 in its simplest form is 2 over 7. So here's the definition. The definition, the simplest form, a rational number A over B is in simplest forms, and we most often say the phrase lowest terms if and only if the greatest common factor between the numerator and the denominator is equal to 1. In other words, there's no common factors between that numerator and denominator. So when the GCF is equal to 1 between the numerator and the denominator, or frankly any two numbers, it doesn't have to apply only to fractions, but when the GCF is equal to 1 between two numbers, it's called relatively prime. It's a important concept. It doesn't necessarily mean that the numbers themselves are prime, but that there are no common factors between the numerator and the denominator or between those two numbers. And here's an example of two numbers that are relatively prime. Let me find my thing. Okay, so let's see. 4 and 5 are relatively prime. Right? And you're like, well, but 5 is a prime number. Okay, let's do 15 and 22. Those are also relatively prime. And they're relatively prime because they have no common factors. Okay, and then I have an example down here that they asked me to find the value of x using the fundamental law of fractions. And what that means, that fundamental law of fractions, is the idea that we can multiply by that magic 1 the same number top and bottom, which will not actually change the equation. So I started out with the problem here. And found that 42 times 5 was equal to 210. So I multiplied the equation top and bottom by 5, which is actually just a fancy 1, right? It's an algebra trick, but it's just a fancy 1. But that gave me 60 over 210, so I was able to surmise that x was equal to 60 because x was originally over the 210, and I was able to change the equation using the fundamental law of fractions to turn it into that equation. So we were able to say that the answer was 60. Now, one of the important things that you'll also start enforcing when you're talking about rational functions is simplifying things down to their lowest terms. We're going to do this by just breaking them into their prime factors. So if I look here at 28, 28 is 2 times 14. 14 is 2 times 7, so 28 is 2 times 2 times 7. We have an A, and B squared is B times B. So this is what we've got over 42 is 6 times 7, and 6 is 2 times 3, so 42 is 2 times 3 times 7. And then we're left with A times A and a B times B. Now we get to cancel things out. One of my favorite things to do. I do like canceling things out. So we get to get rid of some 2's, we get to get rid of the 7's, we get to get rid of one set of A's, and we get to get rid of both sets of B's. And so when we simplify this out, we're left with a 2 on top, and on the bottom we're left with a 3 and an A. Okay. Now the next problem requires us to first factor. We cannot cancel term by term. We can only cancel like factors here. So these x's do not cancel here. What we must do is factor this out. So we must pull out any common factor. Okay, just like up here, we factored it all out. So here we have to factor it out too. This, we can pull out an x. There's a common x, and when we take out an x, we're left with x plus 1. We've been doing this. This is that factoring component, which is the reverse of distribution of multiplication over addition. Okay, so we've been doing this, and then we have it over this x plus 1. Now the only thing to cancel out an x plus 1 is another x plus 1, and it appears as though we have 2 x plus 1's here, so our answer is simply x. So when we get to the next one here, again we must pull out any common factor first. And if you look at the numerator here, there is no common factors. So for now, as far as we will go, I can't say because I am a mathematician and I know that this is a lie, but for now, we can't factor any further. So the key to being able to simplify is you have to be able to factor things down to their most basic units. Let's continue on. This next problem right here, this numerator says a plus b squared. Now remember, on our last example we had that a squared and that b squared, so that means that I write this a plus b 2 times. This is not a squared plus b squared. It's a plus b times another a plus b. Remember what that exponent means. And then if we look at the bottom here, we can factor 3 out because it's common to both of those guys. So if I take out a 3, I'm left with a plus b. And oh, look how nice that is when it all turns out pretty. Now we get to cancel these a plus b's out here, and we'll be left with 1a plus b on top, and you can leave the parentheses if you want, but you don't need to. You can drop them at this point with just a 3 on the bottom. Finally, let's look at this last one here, and if you notice here on top, we can actually factor out a 3 on top. So when we take a 3 out of the top here, we're left with 1 plus x squared over, we can't factor anything out of the bottom, so let's just write it down and take a look. Well, as you can see, there's a 3 on top and a 3 on the bottom. That is a factor here. The operation that's going on between 3 and the 1 plus x squared is multiplication, and the factor and the operation going on between the 3 and the x squared is multiplication. So this is exactly like n times a over n times b. These guys are the same and they get to cancel because this is multiplication. So that leaves us with 1 plus x squared over x squared. Now you may want to ask, or your students may want to cancel these x squares. Those x squares don't cancel because they're not the same. Don't. I have way too many letters in my don't. That was going to be doesn't, and it turns into don't. Let's see. Let's go don't. Cancel. Because of the addition. In the numerator. Okay, look, this thing n is just a number. It can't be anything. It's not something added. It is multiplication. Well, I'm losing my ability to write here. Okay, multiplication in a very bad way. Okay, let's keep on going. All right, another big topic here is the equality of fractions, basically comparing two fractions. That's important. There's a couple of different ways we can do it. I'm going to outline 3. The first way that I'm going to talk about is putting them both in simplest forms. So if we were comparing our 12 over 42 and 10 over 35, we could simplify them out by using prime factorization method here and the fundamental law of fractions, where we can cancel these guys out for both here, and you can see that they're equivalent. So that's one way we can do it. Another way is to rewrite both of the fractions with the LCD. So remember that the LCD or LCM is the smallest number that both numbers go into. So that is, remember, it's the smallest number that both numbers are multiples. So first thing I did here is I figured out what the LCD is, and it happens to be 210. So then I rewrote this equation here. I had to multiply our 12 over 42 by 5 because 42 times 5 equaled 210. And here I multiplied by 6 because 35 times 6 was also equal to 210. And when I did that, I came out with the exact same fractions, that showing that they're equal. Another way that you could do it, and probably the way that I explain it to adult learners for sure, is it doesn't really matter if you have the lowest common denominator. As long as you have a common denominator, you can do the work with fractions and then simplify the answer later. So that's what this idea is kind of going with, is basically just rewrite the fractions with a common denominator. And the common denominator, no matter what, will always be the two denominators multiplied together. No matter what, it won't be the most simple. It won't be the lowest. It won't be that desired one, but it certainly will get the problem solved. And here we note that 42 times 35 is 210. We just saw that a minute ago, but so for 12 over 42, I just multiplied it by 35 over 35, and for 10 over 35, I multiplied it by 42 over 42, and you can see that those also turn out to be the same number. So that kind of brings us to this theorem that clearly my head is in the way of, so I will write the rest of the theorem down here, and it says that two fractions a, b, and c over d with b not equal to 0 and d not equal to 0 are equal if and only if a times d is equal to b times c. All right, now let me make a side note here, just a side point here, that you want to always write your alphabetic variables. So write your alphabetic variables in alphabetical order. Okay, you just want to make a habit of that, and you want your students to make a habit of that. That way they'll see that A times B is exactly the same as B times A. But it'll help a lot if you're just consistent with making that a habit in early days for students. All right. Another thing that's important is for students to learn how to order fractions, decide which fraction is bigger than another. So there is, oh, excuse me. Oh, I slept terribly last night, my pardon. Okay, so there's greater than, there is this definition for greater than a rational number with same denominators, and it goes as this: if a, b, and c are elements of the integer and b is greater than 0, then a over b is greater than c over d if and only if a is greater than c. Okay, and that kind of goes without saying if both of the bottoms, and I'm sorry, I just found another error here, so let me fix this. This is supposed to be a b. This says the same denominators. My goodness, I did a bad job of checking my PowerPoints closely. So this should be a B. My bad. Anyway, here's an example on how, you could explain this to a student, because this definitely comes up. Even for me, I deal with this. A student claims that 1/4 is bigger than 1/2 because 4 is bigger than 2. This is going to be really, really common. There's a couple of ways you can explain it. First off, you can remind them that the bottom number, the denominator, is how many parts the whole is, right? You want to always reinforce that, okay? But in addition to that, quickly you could draw a picture. Now, it's super important that when you do something like this, you have the exact same picture. This is why using paper folding is so good, because every piece of paper, is the same size, and the piece of paper that I have is going to be the same size piece of paper you have, and that way we can make true comparisons. But if you're dealing with things that are not exactly the same, then you're not making a true comparison. So it is important that you make that clear and straight comparison, and let your students understand how important that is. But how do we respond to this? Like I said first, verbally you want to remind them that the denominator will tell us how many parts it is, because you want to constantly reinforce that definition. But also you could make a picture of this, and I used pies here, a round pie chart, but if we color 1/4 of this, so 1 out of the 4 pieces of that, and then we color 1 out of the 2 pieces of this, it's pretty direct. Now, don't ever get discouraged that you have to show a model multiple times. And even if your students are nodding with understanding to you, I would still take the time to show something like this if you have an inkling that even one student is not following what you're saying. It will be fine to reinforce it to those that understand it, and you might finally get through to the one that is not quite sure. Another way is doing this paper folding here, and I am trying to demonstrate the paper folding. So we would have our students have 2 pieces of paper, one piece of paper that they folded into 3 parts, so they accordion folded twice, and then so this would be an accordion fold. And I know I spelled that wrong, but I am not going to try to fix that. There might be 2 C's in accordion, and if I spelled it right, then I'm shocked. But an accordion fold, right? And so that's n-1 numbers of folds. If you need it in 2 pieces, you're just going to fold it 1. If you need it in 3 pieces, you're going to fold it twice, and so forth. So accordion folds are n-1 folds. Okay. So here we accordion folded it twice. Here we accordion folded it 4 times. And we're trying to compare 2/3 and 4/5. So let me just color up 2/3. And then color up the 4/5. Now, sometimes you'll have students want to say that 2/3 and 4/5 are the same, and they might even throw in that 11/12 is the same because they're so close to, they're only 1 away from the denominator, so they kind of try to make that pattern jump, but you can quickly show them with a couple of pieces of folded paper here that without a doubt 4/5 is greater than 2/3. Now this looks, this works effectively, you know, especially for younger students, but even when you get beyond this and half of your class is understanding fractions and the other half of your class is still struggling with fractions, you're going to have to pull from both ends of what you understand as modeling and how to keep your students that are catching on engaged and work on remediating and catching up your students that aren't quite there, especially on the topic of fractions. It really is a rough topic. Now we are going to really lean on the practice of the common denominators, which is one of the easiest ways to make the comparison. So let's take a look here at this theorem. Let A, B, C, and D be elements of the integers with B and D both greater than 0. Then A over B is greater than C over D if and only if A times D is greater than B times C. So let's just take a look and exploit this theorem to compare 2/3 and 4/5. Okay, so first step first is we find the least common multiple of 3 and 5. Because 3 and 5 are prime, the LCM is 15. It's 15 because 3 and 5 are both prime. Therefore, LCM is equal to 3 times 5. Okay, it can't be anything else. All right. Then it says find the equivalent fractions with the LCMs as denominators. So let's first do 2/3. So I'm going to go 2/3. And I need to rewrite that so that it has a 15 on the bottom. And so I know that 3 times 5 is going to give me 15. So this is going to give me 10 over 15. Now let's do our 4/5. I know that from the fact that they're both primes, and we found the LCM, I know that 5 times 3 is going to give us 15. So this is going to be 4 times 3 over 5 times 3. And when we multiply that, we have 12 over 15. And now we can determine that 12 over 15 is greater than 10 over 15. 15, sorry about that. Therefore, we know that 4/5 is greater than 2/3. Okay. Now there's a unique property that emerges when we start talking about rational numbers, and it's the infinite depth of numbers, okay? And what they call it here is the denseness of rational numbers. And the idea is between any two rational numbers, there is at least one more rational number. In other words, between any two fractions, you can find a fraction that fits in between. And in fact, not to blow your mind, but in fact, there is an infinite number of fractions just in between 1 and 1/10. An infinite. We couldn't in our lifetime write down all the fractions that are actually in that little narrow little space. And that's the same if I was talking between 0 and 1 over a million. There's still an infinite number of numbers between 0 and 1 over a million. It's crazy, but that's the denseness of rational numbers, okay? And so here it is kind of technically said that you can always find a number in between two numbers by using this technique. Now, this is a specific technique. This is not, it's a theorem, but you don't want to treat it as something you use all the time. This is very much a specific technique. And it's a specific technique to find a fraction between two fractions, okay? That's the only thing that this is good for. So make sure that you understand that. But it's really cool. So here it is. Let A, B, C, and D all be elements of the integer, with B and D being greater than 0. Also, we're walking into this with the fact that A over B is already greater than C over D. So what it says is that if we add the numerators and we add the denominators together, we will get a fraction that is in between those two numbers. That's what this whole gobbledygook right here says. And so I'm going to tell you what it actually says here, and then, well, I'm going to talk about my warning below. But what this says is you add the two numerators over the sum of the denominators. Okay, and that is going to give us a number in between. I'm going to do an example here in just a minute, but I do want to warn you here. I mean, big, fat, huge warning. Okay, This technique is specific to finding the number between these two rational numbers, between any two rational numbers. And it is cool, and it appears to be a super simple, easy method. And unfortunately, students that are struggling with math will glom on to any little thing that they understand, okay? And so it's important that you do not actually introduce any kind of tricks, and I would consider this without a doubt a trick. I would not introduce any kind of tricks to students until they really, really understand how to do addition of fractions, because adding two fractions together is a pain. Multiplying them is easy and comparatively so, and students just get them mixed up all the time. So I wouldn't be showing any kind of this to students until they were far on advanced and already doing some operations on fractions already. Okay, so, but meantime, it's cool, and let me show you how it works. So, if we wanted to find two numbers between 7 over 18 and 3 over 4, I'm going to use the trick. And the trick is this. Okay, so I'm going to use this trick. So I have 7 over 18. That is greater than 7 plus 3 over 18 plus 4, greater than 3/4. And I just realized I wrote all of my symbols backwards, but at least I was consistent. But yeah, I wrote it backwards. My bad. Last slide. And I feel it. Okay, so now let's see what this is. So let's just clean this up. 7 over 18 less than 10 over 22 less than 3/4. Now, we could trust this because I told you that it works, but let's check. All right, let's just check. Now, the way that we need to check is we need to get all these to have common denominators. Let's check by getting common denominators. This is a great review. So, first things first is I'm going to take my 18, my 22, and my 4, and I'm going to get the prime factors of those. So 18 is 9 times 2, and 9 is 3 squared, so 18 is 2 times 3 squared. 22 is just 2 times 11. And 4 is 2 squared. Okay? Now, if you recall from last chapter, our least common multiple of 18, 22, and 4 is the highest power of all the primes that are represented in the prime factorization. Okay? So, we're going to need the 2 squared, we're going to need the 3 squared, and we're going to need an 11. This is what our least common multiple is. Okay. Now I like to write it like that because then I don't have to think as hard when it comes to what do I need to multiply by 18, by 22, and by 4 to get what I want them all to be. Okay. So let's check that next step out here. So 18 was 2 times 3 squared, what do I need to add from this list above here that we're missing? Well, I don't have a 2 and I don't have an 11, so I'm going to have to multiply that guy by 22. Let's just keep on going here. 22 was 2 times 11, and what am I going to need to multiply that by to get our LCM here? Well, it looks like we need another 2. We don't have the 3 squared. Finally, what do we need to multiply this 2 squared by, our 4 by, to get our LCM? Well, we have the 2 squared, so we would have 3 squared times 11. Now, when you multiply all that out, I think it's equal to 180. Pretty sure that maybe it's not equal to 180. Because I changed my example. Let me just check real quick. 4 times 9 is 36 times 11 is 396. Okay. And I only wanted that number so we could put it together all nice and pretty here. Now, so this is our denominator for all 3. So now let's put it together here. So we've got 7 over 18, and we determined we need to multiply the 18 by 22. So whatever we do to the bottom, we got to do to the top. So we're going to have to do 22 on top and 22 on the bottom. And then I'll put our sign back in here. And let's look at our 10. What are we going to have to multiply that one by? It looks like we have to multiply it by 9 times 2, which is 18. So this one's going to be multiplied by 18 over 18. And that was 10 over 22. We're just making this comparison to make sure that this works. That's all. Plus, it's good to practice all these things. And then finally, what do we need to multiply that 4 by? Looks like 9 times 11 was 99. Remember, we're using that fundamental law. So we're just multiplying the same number over the same number by our fancy one. That's over 3/4. And then when we do that final math, and I think I already did it, we wind up with 154 over 396 is less than 180 over 396 is less than 297 over 396. So it worked. Kind of cool. All right. Thanks. Y'all have a good day.